methods, and then later on, maybe in the next class, we will look at actual calculation, right? So at the beginning, first of all, people, as I mentioned earlier, with the gambling, what they do define was they defined first of all they defined the concept probability of some event, and then they mentioned several ways of calculating. So the early method was called the classical method. That was applied only for particular type of problems, not always for any problem, right? So the classical probability is called classical probability. So it's a method of calculating probability, way of calculating probability. It's called classical or a priori. There's a definition or method of calculating. In this method, we can calculate the probability of some event. Now we know that event is always a subset of some sample space. This is where that definition is important. It's always a subset of some sample space. So once you know that my event is a subset of some sample space, then I can talk about some conditions. Right? See whether the sample space is a finite one. That means the number of outcomes in the sample space is finite. Then whether those outcomes are equally likely, right? So this is a problem a little bit, because in order to define or calculate probability, we need again a probability idea, right? Equally likely means again the idea of probability. So that's a weakness of this probability, this definition, but still that's a kind of a feeling that we have to have. Right? So in order to check whether or decide whether these outcomes are equally likely, whether even we have probably sometimes we have to think or ask the question, is there any reason where these outcomes can be having different possibilities? Is there any way that these outcomes have different possibilities? Right? If there is no reason for us to think that possible outcomes have different possibilities, then it's reasonable to assume that they are equally likely. So like that. Or maybe there is some technical word we use. Okay, assume that you are using a fair coin. Right? So once you use the word fair, then we give the idea that they are equally likely. Assume that you use a fair roll, a fair die. So fair die. There's nothing called fair die or fair coin in the world. But in order to fit this into this framework, we use the word fair in that case. Or otherwise, in practical situations, we have to ask ourselves the question whether there is any reason for us to believe that there are different ways, different possibilities of these outcomes. Right? So if there is no reason to believe such a thing, then probably we can safely assume that they are equally likely. So somehow we have to have some idea whether they are equally likely or not to use this method. So this first second condition is we should at least feel that they are equally likely. Outcomes are equally likely. Finite, equally likely. So those are the two important things. So if these conditions are satisfied, then of course the probability of that event is defined as the number of outcomes in our particular event. Our event is a subset, so there are a number of outcomes, we can count them. Number of outcomes, that is what you mean by the number of outcomes favorable to A. In other words, that is the same as number of ways that particular event A can happen. Right? So if for example A has 3 possible outcomes, even number means 2, 4, 6 for example. So one possible way to happen A is having a 2, another possible way to having even number is having 4 and having 6. So there are 3 ways to have even number. So that is the same method, number of outcomes in set A divided by the total number of outcomes in the sample space. So that is the definition of the classical probability. So in order to calculate the probability of some event using the classical probability, we don't have to actually carry out any experiment. We don't have to roll the die. We don't have to toss the coin. Right? It's enough for us to know what are the possible outcomes. It's enough to know the sample space, and it is enough for us to know what are the outcomes in our particular event. And then we can check whether the conditions are satisfied, and then we can calculate the probability if the conditions are satisfied. අපිට ඇත්තටම මේක රෝල් කර කර බලන්න ඕනේ නැහැ. ඒක දෙයක්. අනිත් මෙතන සුළුදී අපිට එක්ස්පෙරිමන්ට් එකක් කරලා බලලා දත්ත අනුව තමයි එන දත්ත අනුව තමයි probability එක හොයන්නේ. Right? So we have to do the experiment. In this case we don't have to. But then in order to find out the number of possible outcomes, as he said, we have to look at, for example, sometimes combinations, permutations, right? In order to find out the number of ways, hold the sample space, number of ways, number of outcomes in the sample space, and also the number of outcomes in the A. In order to find out those things, we need mathematical rules. So we will probably talk about those things a little later. Right. So that's the first method. Of course, this method cannot be applied in practical most of the situations, like rolling dice, tossing coin, or balls, for most of the practical situations, you cannot actually use this method, classical method. The second method is the most practical method, that is called the relative frequency method. Relative frequency method. So in order to calculate the probability of some event using this method, you have to actually carry out your experiment. Right? For example, suppose to take a very simple situation, suppose you have a coin, but you don't know whether it is a fair coin or not. Right? Nobody has told you that it's a fair coin. Maybe there is a possibility that one side has a higher chance of coming up. Right? So if that is the case, and suppose you want to find out the probability of that side coming up, so then how do you find out the probability? You cannot use the classical probability now, because there are two outcomes, head and tail, but one may be having a higher possibility, so they are not equally likely or probable. So in that case, there is no way, no other way. We have to toss the coin large number of times. Right? It's not maybe enough to toss 5 times and then find out how many times head came. Right? So you have to do your test large number of times and then find out how many times your particular event occurred. So then divide the number of times your particular event occurred by the total number of times you did the experiment. So that is called the relative frequency of your event. Right? Frequency is the number of times that event occurred. Relative frequency is that frequency divided by the total number of experiments. So the relative frequency is used as an approximation to the actual probability. There is an actual probability of getting head for that particular coin. We don't know that value. And we will probably not able to find out the actual value ever. Probably. What we can do is only estimate it. Estimate the actual value using a fairly large number of experiments. So this is called the relative frequency method. Right? So this comes from a certain definition of the probability called the relative frequency definition. Right? So the definition of the relative frequency idea, relative frequency notion, we call it, relative frequency notion of a probability of an event. This can be applied only for those random events which can be repeated again and again and again. So suppose you can repeat your experiment. In any experiment, either your event occurs or it doesn't occur. Right? A event එකේ තියෙන outcome එකක් එන්නත් පුළුවන් අපේ experiment එකේ නොවෙන්නත් පුළුවන්. ආවොත් අපේ event එක සිද්ධ වෙලා නැත්තම් නැහැ. Right? So in each experiment, either your event occurs or doesn't occur. Right? So therefore, in at each experiment, you can calculate by that time how many times your event has occurred. And if you divide that by the total number of times you have done the experiment up to that point, so at that point, that is the relative frequency of your event. අපි දුම් 10 පාරක් කාසිය උඩ දැම්ම 3 පාරක් කාසියේ හෙඩ් එක ලැබුණා කියලා 10 වෙනි පාර එනකොට එතකොට එනම් 3 divided by 10 is the relative frequency of head at that point. So 11th one there will be a relative frequency, at the 12th one there will be a relative frequency, like that. If you look at the sequence of these relative frequencies, right, you will see that when n goes to infinity, this sequence of relative frequencies is converging to some number. So that number to which this relative frequency, sequence of relative frequencies converge, is defined as the probability of the event. So in this notion, the probability of an event is defined as a limit of the relative frequency as the number of experiments goes to infinity. So it's a limit. So mathematically that's how you define. So here Fn A is the frequency of event A at by the nth experiment, and divide by n gives you the relative frequency at the nth experiment, and then probability of the event is defined as the limit of this sequence of probabilities. So it's a limit actually. We will never be able to actually see this value. We don't know what this value is going to be because n has to go to infinity, right? But that is a definition, right? So what we practically do is actually, because we cannot do anything infinitely times, we do it as much as practically possible, and then take the relative frequency at that point as an approximation to the probability. So it will not, it has not gone to the limit yet. But when you increase n, it will be coming close and close to a value. So let me show you some result that I got from a simulation. So I looked at some event. I think I designed my event so that the actual probability I know of that one, like 0.3. So what I did was I carried out this particular experiment using the computer program. I calculate the relative frequency of a particular event at each step, right? So you can see that at the beginning, at the first one, it was like 1. That means in the first experiment, my event occurred. So at that point, the relative frequency was 1 divided by 1. Right? So it's 1. And after that, in the next one, it didn't happen. Therefore, in the second one, the relative frequency becomes 0.5, right? 1 divided by 2, like that. At the beginning, it has a big fluctuation. Relative frequency is fluctuating very much at the beginning, right? But as the sample size becomes larger and larger, you can see that it's converging to some value. Right? So this will theoretically converge to some number when it goes to infinity. That is what we define as the probability of the event, according to this notion. Right? So what we practically do is actually, maybe we will stop somewhere here, the experiment, and take whatever this value as the approximate value for the probability. So that's how you calculate the probability in that case. Only thing we have to know is that it is not the actual value. Actual probability is only approximate value. Whereas in the classical method, if those required assumptions are satisfied, that will be the actual probability. Right? If a coin is a fair coin, for example, getting a head probability is exactly 0.5. Right? If a dice is a fair die, probability of getting an even number is 0.5 exactly. Right? So in that case, it's exact. So once you get a value, like once you find out the probability, you get a value, probability, you'll see that later on, it's a number always between 0 and 1. So that's how the probability is defined. There are some axioms that define what a probability is. Right? According to that, probability must be always 0, between 0 and 1. Some people report the probability as a percentage, which is actually wrong mathematically. Probability is probability mathematically conceptually it has to be like 0.75 in that case. right? But many people don't know that mathematics into that level, so they just say it's a 75%, which is mathematically wrong, because probability by definition has to be a number between 0 and 1. Right? It cannot be a percentage. Right? But anyway, so once you get a value between 0 and 1, like let's say you got a value like 0.7 as a probability of some event. So one can ask, what does that mean? How do you interpret this value? Right? So we should be able to interpret also. Right? So if you are using this relative frequency notion, you can say it is approximate. It's not exactly. It's approximately the relative frequency or the proportion of times your event, my event, this particular event A will occur if I repeat my experiment large number of times, again and again and again. So those words, large number of times, is important. Right? If I repeat my experiment a large number of times, then approximately this proportion of times my event will occur. That's what it means, right? So if the probability is, the answer is 0.75, then you can say this means if I repeat my experiment a very large number of times, approximately 75% of the times this event will occur. That's what it means. Right? So like that you should be able to interpret also. So that's called the relative frequency interpretation. In the long run, right? So that's what I mean by if you repeat the large number of times. The probability of an event is interpreted as the long run proportion of times that the event would occur if the experiment could be repeated indefinitely under the same conditions. Could be repeated indefinitely. Right. And then of course the third method is the subjective method or the Bayesian method, which is not a topic in this book. That is what people use especially to talk about events which are, the probability of events which are not repeatable. Like one might ask, what is the, if I suppose there is a patient, doctor says you have to go undergo an operation for something, and his relatives ask what is the chance of getting surviving after this thing, right? So still we are interested in the chance, right? What is the chance of having a good result after this, right? So, but now we cannot talk about relative frequency notion of probability, because we cannot operate several times and see how many times he gets better or survives, right? But still we should be able to say, okay, something, and we have, the doctor will in that case use his experience, right? So he will probably think of similar patients on which he has done this particular experiment, at similar type, similar age, similar type of patient, and out of those how many were able to survive and so on. So he will use his knowledge, proportion, and he will express it as a proportion, or probably he doesn't know probability, so he will express it as a percentage, right? So in that case, if it is a percentage, you cannot use the word probability, but you can use probably chance, word chance. Right? Because probability for us is now is going to be a technical word. It has to, it's a function which has certain properties. We talk about that, something called Kolmogorov axioms. Right. But this kind of probability, one doctor may have one value. If I go to the another doctor, he might have a different value. Right? So it's a subjective probability, right? According to his experience. Right? So there are ways of getting that kind of probabilities using some prior information, using some Bayesian theorem, Bayes theorem, and so on. But it's not a part of this one. We are going to talk about only classical method and the relative frequency method in this class. So the next method, as I mentioned, as you for your question, is the model based. So what we are going to do, especially these are important for the discrete case also it's important, but mainly for the continuous cases. If your observation is of continuous type, usually we assume some model for the distribution of your observation, right? So in order to assume that, you have to have some data, of course, or maybe some prior information about the shape of the distribution, right? The shape of the histogram. If you collect some data and draw the histogram, what would be the shape at least? Or maybe if you have the data, then you can plot the histogram and see the shape, mainly whether it is bell shape or whether it has a long right tail or left tail or whatever. Depending on that, there are large number of mathematical models developed by people, right? So normal distribution is one model developed by people. There are so many other models of gamma distribution, exponential distribution, Weibull distribution, so many other distributions. If you want, you can come up with the model 2. Only that you can put your name on that. Only thing is that that's a mathematical function, and the area under that function has to be 1. That's the only requirement, and that can be defined as a mathematical model for a probability distribution. Whether it's a practically useful one is a different thing, but mathematically it can be a probability model, right? So there are so many models like that, depending on the skewness, depending on the curvature and so on. So select one of the suitable models and then use that model to answer your questions. Once you assume that it has, say for example, my random variable x has a normal distribution with this mean and this variance, then I know a lot of things mathematically about the model. So I can use those properties to calculate probability, find out quantile, so anything. So that is the last method to calculate the probabilities. So we'll talk about this model-based one also in the next chapter, I think. So if it's a discrete one, we will be integrating the density function or maybe using some other formulas, right? So this last one actually is not a method of calculating probability. It is actually the definition of the probability, axiomatic definition, right? So if some function, right, this probability can be thought of as a function also, right? So because we write down PA, right? So in the elementary level, we just interpret this P as the first letter of the word probability. So it's probability of A. But actually, this can be considered as a function like fx, right? So f is the name of the function and x is on where we evaluate that function. Similarly, this p can be considered as a function, and this is in that case a set function. We evaluate this function on a set. A is a set. So therefore, probability is a set function, right? So any function, any set function can be a probability function if these conditions are satisfied, right? So Kolmogorov, who first defined the probability like this, have set up several conditions for some set function to be a probability function, right? So there can be various functions, like for example, there is a function called Px. I'll come to that later. So what are the requirements for a function to be set function to be a probability function? First of all, when you calculate the value, if you evaluate your function p on a set, on an event, in this case we are talking about events, it has to be a positive value, non-negative value. It can be 0 also. So it has to be non-negative. That is the first requirement. The probability of any event is always greater than or equal to 0. And then the probability, when you calculate that function on the sample space, the answer should be 1. That is the second requirement. The probability of the sample space should be 1. The third requirement is called the additivity, I think, yes. If you consider several mutually exclusive subsets of your sample space, and if you calculate the probability of the union of those subsets, that should be equal to the sum of the individual probabilities. Right. So if there is any function p satisfying these three conditions, that can be considered as a probability function. Right. So that's how you define a probability function. Probability. So these axioms do not help us to calculate the probability, but once you have some function, you can check whether that is a probability function by checking whether these conditions are satisfied. So that's why I said we cannot use the word probability like a layman always when you are in this kind of class. Now probability has a meaning. Right? So it has to be between 0 and 1. These three axioms will imply certain other properties. One such property is probability of any event is always between 0 and 1. That is coming from these three. You can prove that. So right, once you say probability of any event is greater than or equal to 0 and probability of the sample space is equal to 1, those two will imply that probability of any event is always between 0 and 1. Right? Inclusive, they can be 0 or 1. Right? So therefore, that's why I said whenever we talk about probability, as a mathematician, we should never say probability is equal to probability 75% or 80% or something. But as a percentage, we don't mention probability. It has to be a number between 0 and 1 decimal number. But I have seen in a lot of books also, they say write down the probability as a percentage. Right. Are you tired? But the other topic is the condition and probability. I'm telling you, any break. Navattala me. Another is correct. That. You know, correct thing that. කලින් තමයි නවත් තැන ඒක හොඳයි. ඔය කියලා තියෙනවානේ මේ විනාඩි 40යි යල්ලන්නේ කියලානේ. ස්ටුඩන්ට්ට ඒක දිගට.
Share something.
Yeah, okay, let's stop now. If you